This is the President's Lecture Series. Started with honor a professor, and indeed we're honoring a professor today, someone who's earned the respect of their colleagues, a teacher, researcher, and a mentor, Professor Adrian Leighton. Professor Leighton instructs us that he has a bachelor's degree in anthropology, and after working in archaeology and cultural resource management, he then began graduate studies in forestry. He started teaching forestry at Salish Kootenai College in 2003 and received his PhD in forestry from the University of Massachusetts in 2005. In 2005, Salish Kootenai College became the only tribal college in the nation to offer a bachelor's degree in forestry and currently has over 60 students from 15 different tribes. So hooray for us and hooray for Professor Leighton. Professor Leighton is also the co-chair of the Intertribal Timber Council Research Subcommittee. He lives in Ronan with his beautiful, gracious wife and his darling little girl. And his title today, I think, is A Forest for the Trees around forest health. And so with that, please welcome Professor Leighton.
Thank you very much, President Ross, and it's an honor to be here. Thank you for coming. So today's the lecture is it's a little tongue-in-cheek, the title, but I think it's incredibly important when we talk about forests, and especially about forest management, as the landscape changes both through human activity and through other changes in climate, both human-caused and other cycles of change, that we keep in mind that a forest is made up of trees, and how individual trees grow and how they compete with each other is the basis for everything that is done in forest management, whatever the objectives may be. So change is a major theme for today. And there's change on a lot of different scales. The current forest health and composition has been greatly impacted by human management over time. And there has been a lot of change in terms of how we do that management, in terms of our perceptions of what works, in terms of our goals and objectives. My colleague, Professor Pat Hurley, has a great slide that she uses in classes. It has a picture of a moth on a tree trunk, and the caption that she uses with it is, "I've been here my whole life and nothing's changed at all." And I think that's important for us to keep in mind too, because as humans, when we're managing a resource like a forest where the average lifespan of trees might be 4, 5, 6 times longer than our own, we see a small piece of this evolving change or this dynamic across the landscape. And keeping that in mind and understanding how that works and adapting to it is critical to forest management or to any of our relationships with the forest. So people have been part of the landscape for a long time. And some of the perceptions we have, especially in forest policy at a federal level, like the Wilderness Act, which says that wilderness is a place where man shall only be a visitor, tends to forget that people have been part of the landscape for thousands of years. And we know in the northern Rockies and throughout much of the United States, the traditional use of burning as a management tool by tribes, has had a big impact, especially on certain stands at lower elevations and in various contexts. And there was a lot of different reasons for burning. As a wildlife management tool to increase browse, to clean out understory, to help regeneration of berries and medicinal plants and other medicines, to make it easier to travel across different routes through the mountains. So there were a lot of reasons that fire was used. Later on, our management strategies changed, especially after colonial impact and the movement of this sort of more Western paradigm of management moved across the country, and starting with the fires in 1910, certainly, and by the 30s, there was a full force on this reservation and throughout the country policy of putting out fires. This is a time when management was really about trying to figure out some kind of sustainable yield of timber products. It was about getting timber out of the woods. In management, in its best case, it was about trying to do that perpetually in a way that didn't harm our ability to get access to timber later, but a lot of it was about timber yield. So fire suppression was partly because there was this reaction that this was fire was a waste of the resource. And so we had a full-on policy of fire suppression that has had impacts to forest health over the last century. And past forest management strategies have also had a big impact on forest health, both good and bad. In some cases, it's created stands that are more able they have more resources and more able to defend themselves from pathogens. In some cases, what we've done, and this is another recurring theme of this presentation, is we created kind of a homogenized effect across the landscape where we have a lot of trees. Because of the way we manage for sustainable timber yield, we have a lot of trees in a relatively few number of age classes. We've simplified species diversity in some cases. We've simplified age class diversity. And we've created situations where trees in some cases are more susceptible to stress and therefore more vulnerable to attack from insect and diseases. So what's happened then is we have 100 years of management that in some cases have set up increased vulnerability, and then especially in the last 30 years where there's been a rapid acceleration, a very different time scale from that of a tree. In a very short period of time, climate change has added stresses, drought, temperature changes, fire intensity changes in how bark beetles and other insects live their lives. It's aided invasive species in their spread because of the stress to the native plants. It's created a second and sort of exacerbating or magnifying stress on the ecosystems. So, but what I'd like to do is start with, in order to really understand this, especially this role of density, tree number, and stress, is talk a little bit about how a single tree grows. Trees are remarkable. They're really amazing. If you think about it, they do everything that any animal needs to do in order to survive. They make food, they deal with waste, they make decisions about how to allocate energy, they defend themselves from predators. They do all of that without ever leaving one single spot. When you think about that, that's pretty incredible. They don't like the neighborhood, they can't move. So they have to deal with the environment of where they are, and they have some pretty amazing adaptations to that. But ultimately, what a tree needs in order to survive and grow are just a few things. It needs sunlight, carbon dioxide, and water. So photosynthesis is essentially, in simplified process, sun is the energy used to take apart carbon dioxide and water molecules, to split them and recombine them into a glucose molecule, into sugar. So with sunlight, water, and carbon dioxide and the nutrients needed for plant life, this is pretty much a tree is able to manufacture its own food base. It needs physical space, and collectively we use all of these terms. In silviculture we talk about growing space, and this is the kind of sum total of all of these things. The amount of growing space that a tree has is its relative amount to other trees of the water, the light, the nutrients that it needs in order to survive. Now, what we know about trees is they, just like people, they make investment choices. So as they make this food, as they take that light and water and carbon dioxide and turn it into sugar, they essentially have to choose how to invest it. And those investment strategies start pretty much with height growth, especially if you're a tree that doesn't tolerate shade very well. The first thing you want to do is grow tall enough so that you're accessing more sun, or so your neighbors aren't shading you out. Because if you get sunlight and carbon dioxide, you also need water. Your second investment then is going to be in your roots, to make sure that you have enough water to keep those leaves up in the canopy photosynthesizing. If a tree starts to run out of water, the first thing it does is it actually shuts down the stomates, which are little pores underneath the leaf that bring in carbon dioxide, but water vapor leaves through those holes at the same time. So if the tree starts to run short of water coming from here, it's going to shut down its ability to photosynthesize up in the canopy. So keeping that supply chain balanced is very important. Storage, to some degree, depending on the species, is next. Diameter growth, and then kind of lower on the list, because they're very expensive compounds often to create, are your defensive chemicals, the terpenes and the pitch and all the different compounds that'll help protect the foliage, either make it hard to eat or waxy protective layers, or pitch that will force bark beetles out of the pine trunk. Those are actually at a relatively lower priority of investment than some of the other things. So ultimately, when we look at healthy forests, forests that are healthy are getting, the individual trees are getting enough resources to be able to invest fully down their investment chain. If I sound like an economist, my father taught microeconomics at university for 30 years. So I think even when I first got my allowance, I was told about opportunity costs and things like that. So, but the tree is making sort of investment decisions. Now, if we take how a single tree grows and we talk about how groups of trees grow, we kind of scale this up to patterns. One of the things that I think many of you might find this familiar is this pattern of forest succession. And this is, again, kind of recognizing that forests are dynamic systems, that they change over time, that there's this gradual replacement of our shade-intolerant trees, which, because they need sun, they tend to grow very, very quickly. They tend to grow very straight. They often have relatively small crowns because the lower part of the crown gets shaded out by the upper part of the crown. They tend to be species, and larch is a good example, or lodgepole pine, to some degree ponderosa pine. A lot of the hardwoods like birch and cottonwood are other excellent examples. And they grow very quickly, they grow very tall, and they tend to be relatively shorter lived than the more shade-tolerant trees. So what we see in this kind of classic pattern of succession that was described by Clements, originally Frederick Clements at the turn of the century, is this pattern of fast-growing shade-intolerant trees racing up into the kind of establishing a canopy, and shade-tolerant trees, which tend to live much longer and grow much slower, building up underneath and slowly replacing them. So as these trees, maybe they live 100 or 150 years old, as they start to die individually, more light's making it down into the understory, and those shade-tolerant plants, who tolerate shade, but still, if they get more light, will be able to take advantage of it. They'll move up into the canopy. And because they're capable of reproducing in their own shade, you'll get another generation of those shade-tolerant trees underneath, and they'll replace as individual older trees die. And this creates what I think most of us think of as an old-growth forest. This pattern of shade-tolerant trees, long-lived shade-tolerant trees living underneath each other. And around here, the best example of that would be, say, a cedar grove, where you have grand fir and cedar. You have multiple layers of canopy because you have trees of different ages growing up underneath each other. Wind throw or something like that knocks down a tree, creates enough sun for one of those trees in the mid-strata to move upward. And that system, according to Clements in his successional model, will continue because he calls it climax because or steady state phase, because it'll keep happening until there's a big disturbance that hits the reset button. That big fires, say, that takes out that grove. Maybe that happens every 500 years or 400 years. And that stand burns down, and then seed from the wind of shade-intolerant trees comes in, and the whole pattern starts all over again. Now, this is a useful model, and it does happen in some places, and in other places it would happen if it weren't interrupted, but it doesn't account for disturbance except on a 500-year interval. And we'll get back to that in just a minute, but that is one of the, especially in the Rocky Mountain West where there's a lot of fire behavior, this is a critical flaw in this model. So in early succession, early on after a big disturbance, and this is a little clear cut from Boulder Creek area on the east side of the lake near Finley Point, you see we're already sort of starting to see this pattern. The more shade-tolerant trees like Doug fir, which is kind of a mid-tolerant species, a little bit shorter, you get your lodgepole and your larch growing a little bit faster. So after disturbance, there's all this growing space is released. The overstory is removed, so there's no longer any hold on the growing space from the overstory. So all the light, all the water, all the nutrients are available for a new generation of trees. The shade-intolerant trees grow quickly, and once there's enough of them and they grow tall enough, they create a closed canopy. Now this is a period that in stand dynamics and silviculture we call stem exclusion. And this is a very important time in the life of a stand. It's a very major shift ecologically and change in the life of that stand, because in this stand structure you can see that there's a lot of herbaceous plants and flowering plants. This is a great time for wildlife. There's a lot of browse low to the ground where they can get it. This is usually some of the highest diversity of plant life in the history or in the lifetime of a group of trees. But once the shade-intolerant trees kind of grow up and create a closed canopy, the light levels on the understory drop to maybe 8 or 10% of what's hitting the top. So from here, 90% of the sunlight's absorbed by the time it gets down here. So we see a very quick drop in diversity of the understory, And a lot of what's happening in the stand is competition between individual trees in the overstory. Because what we know, and this is a universal law that, that has been discovered in plant communities throughout the world, and this is my flashy scientific graph for the day, but if you have a number of individuals, high number of individuals going to low individuals, and you talk about individuals' biomass, so that could be diameter, breast height, or total size, or total weight, as basically as each individual gets bigger, there can be fewer individuals in the stand. And this happens, in just about any relationship, and especially when you think about trees and how they can't move. You may start off with a clear cut that's got 2,000 trees per acre. If you were to go back to that stand 150 years later, you might find 300 trees per acre. And that's because as each tree needs more resources, the sun's not going to shine brighter, it's not going to rain more. There's a partitioning of resources. So, we use the term competition. Trees compete with each other. I mean, it's kind of a very anthropogenic term, but there certainly is a finite number of resources. And as each individual requires more, the number of individuals is going to drop. This will happen in the stand whether humans are involved or not. So as this process happens, though, this is a time of a significant amount of stress for trees because it tends to be a slow process of some trees kind of falling behind others and getting overtopped and shaded out over time, or being a little bit weakened and disease coming in and kind of thinning out the stand. Once that pattern kind of goes through, the shade-intolerant trees, once they get to a certain age, they kind of slow down. Their growth rates slow down. They're spending more of their life as they get into 80 years old or 100 years old. More of their energy is just being kept in maintenance and in respiration, and less of it in overall growth. And as those individual shade-intolerant trees die, as I said earlier, the shade-tolerant trees move up into the overstory, and eventually we get a stand. This is a cedar stand from North Crow, where you have a lot of different strata in the canopy. You can see little trees and bigger trees, and trees growing up underneath trees. This is the beginning of the creation of an uneven-aged or all-age stand. And as individuals in the canopy get blown over this shallow, wet soil, wind or other activities will take out a small group of trees, and that's going to create enough light for some of the species, some of the individuals that are kind of in the understory to start to move up into the overstory to take advantage of that light. And when you go into especially a cedar stand, there's this thing that we call pit and mound topography. When you walk through a cedar stand, you'll see this rolling topography. And what that is it's thousands of years of this superimposed on each other. There's going to be a pit where the roots came out. As this decomposes, it's going to create a little mound. And as you walk through cedar stands, you can see some of them are very old and they're kind of fairly moderate, but if you look, you can see this sort of rolling swale to the cedar stands. And it's just basically patterns of this happening over and over again across the stand for hundreds of years. So this is kind of Clemens's climax. And in stands where there is not frequent disturbance, these are our structurally diverse, multi-layered, old-growth stands, very important for wildlife. Very important kind of ecological values, and there are very particular plants there that also often have a lot of cultural values. The thing about succession, it was always one of my favorite, was that seatbelts is not just a good idea, it's the law. Well, we tend to think of succession the same way. And we tend to sometimes get hung up, I think as foresters especially, or as ecologists, by this sort of naturalistic fallacy that just because something tends to happen, we think it should happen. Now, succession will happen in most stands if disturbance doesn't interrupt it, but that doesn't mean that that's not a naturally appropriate or right thing. We talk about stands where fire comes in and changes things before succession can get all the way through to climax. The official term for that is arrested succession, as if this was somehow kind of a bad thing. But what we're really starting to understand as we look at the ecology and the past history of a lot of these forest stands is that this straight line succession is a process that explains potential. This can happen in these stands, but it doesn't mean that it should happen or that it frequently did historically. So in the succession model, disturbance only comes in once it's a full disturbance, it hits the reset button, we start through succession all over again. So it's a straight line that loops back. But what we really know now is that in a lot of ecosystems, disturbances are a lot more prevalent. They don't happen once every 400 or 500 years. They might be happening once every 8 or 10 years in ponderosa pine forests with low-intensity fire. In New England, we recently found that there are major hurricanes that occur on about a 100-year interval. The last one was in 1938. It knocked down 70% of the standing forests in central Massachusetts. So that was a pretty major, but it didn't knock over everything. It left a lot of patchiness on the landscape. So as we look at disturbance, and there's a fairly new field of disturbance ecology that shows that the Clements model is great as a theoretical, but in a lot of cases, disturbances, partial disturbances or more frequent disturbances, kind of keep it from happening. And getting back to kind of where we're going with this connecting into forest health and this thing about density that we just talked about is that forest management, both active management on the land through timber harvesting and through fire suppression, has created a lot of stands that are in this denser, earlier successional phase, this stem exclusion phase where there's a lot of competition, higher stand densities. A lot of the management activities that we have done over the last century has tended to move a larger portion of the landscape into these stand conditions that are also the most vulnerable to a lot of forest health issues. So this is just an example. This comes from the Confederated Salish and Kootenai Tribal Forest Management Plan, which is almost a textbook in ecosystem management. In fact, it could be used as a textbook, put together by Jim Derglow and a bunch of other experts, written by Dave Rockwell. It's available online, actually, at the CSKT website, and it's a really well-written management plan. And this kind of is just a graphic that sort of explains the role of fire, especially in lower elevation stands here in the Rocky Mountains. I'd be happy to put this up later. But again, what we see is that fire doesn't just follow one particular straight line. Fire at different times is going to create different stand conditions. And a lot of what the tribe is trying to do now in forest management is look at the history of those different stands and figure out what role did fire play in the past, how frequently did it come in, at what intensities did it come in, and then either put fire back into those systems or at least manage it in a way through harvesting and other active management that kind of recreates those stand structures. So basically, this I guess is a summary, but this 100 years of fire suppression has really allowed this clemency and succession, which didn't normally happen over a lot of our landscape, to occur on our landscape. So we have more trees in some places. We have a higher density of shade-tolerant trees than we used to. In lower elevation pine stands, what we kind of know now, here at the elevation of the college, at about 3,200 feet, and as you get into the lower missions, these were, in a lot of cases, were dominated by stands that were tended to be a few kind of widely spaced older ponderosa pine trees with a grassy understory, maybe a 15-year return fire interval. There wasn't much time for fuels to build up. It was fairly grassy. So the fire would move quickly through that stand, kill off a lot of the shade-tolerant regeneration like Doug fir or grand fir. Some of the pine regeneration, let other pine seedlings would survive and grow up and to replace the occasional tree that died. But these were frequent, quick-moving, low-intensity fires. And it left a fairly open pine stand that was dominated by larger trees. As we put out fires in these ecosystems, we've created a carpet of Doug fir, which is more shade-tolerant, building up underneath it. And over time, those Doug fir are replacing the ponderosa pine, and we're getting to a stand conversion where the historically appropriate species, the species that had been here primarily for thousands of years, ponderosa pine is being replaced over time by Doug fir. And this also sets up the conditions for a very different type of fire event. When you have dense Doug fir stands at higher densities, then the chances of a severe fire, a crown fire instead of a surface fire, the probability increases greatly. This is a Forest Service picture. Some of you may have seen that a couple of these are fairly famous, but it shows this is a pine stand, again, this open grassy condition. The Doug fir started to come in after fire suppression. And this was 1895, and then you're getting a stand that is increasingly dominated by the more shade-tolerant Douglas fir. So we're getting higher densities, different species. So it changes in lower elevations. This again is from the management plan, the tribal management plan. You can see that historically from 1945, the percent of the forest was high to pine at lower elevations. Doug fir is slowly taking over or replacing it. So we're seeing a species shift. We're also seeing a shift in size classes. Again, this is primarily through active management, but also the buildup of the Doug fir, the seedlings, and the small trees that are coming in underneath those pine stands. That's actually probably a bigger cause, is succession occurring and the shade-tolerant trees building up. We're seeing a greater number of small trees and a declining number of large trees at lower elevations. This is just a picture from North Crow. Again, you can see the kind of a more open pine stand with the carpeted Doug fir coming in underneath. A lot of active management in this area right now is trying to open up these stands, thin them out so that the fuel loading is not too heavy, and then get fire back in there to try to kind of restore them to a more open, grassy, what we consider to be a more natural, ecologically appropriate condition. What this means in terms of forest health and in terms of diversity is that over time we're really losing what we call landscape mosaic patterns. So this is you can see that because of fires and other practices, there was a real patchy mosaic of clearings and of different age classes, a lot of small stands of different age classes and different stand conditions and structures across the landscape. Here's another picture of the mission, St. Ignatius Mission area. I believe this is 1920s and this is about 1995. So you can see that there has been a fairly significant change in we've created a much more homogenized environment. It's almost like someone's dropped a blanket of trees across the landscape. So we've lost a lot of our patchiness. We've lost a lot of our landscape diversity through a combination of fire suppression and management. Some of these lower, we're not entirely sure, but some of these is probably a combination. Fires up top, some of these gaps down lower might have been more timber sales in the 20s and 30s. The BIA really saw that when the Division of Forestry for the BIA started around 1910, their trust responsibility, especially in forestry as they interpreted it, was generally, hopefully a sustained yield, but primarily it was they concentrated on the economic side. They really saw their responsibility to the tribes to employ tribal members in the woods and to provide the tribes with income through the use of forest resources. You can argue long-term, especially in the 20s and 30s, whether sustainability was as much of a picture as it should have been. But this is million board feet. This is the annual cut during the BIA's tenure here on the Flathead. The tribe now manages, of course, the resource. Their annual allowable cut's right around 20 million board feet. You can see that there are times when the BIA is cutting both in the 70s and 80s, and some of this is what led to the creation of the Mission Mountain Wilderness reaction to that, and especially in the 20s up until World War II, often tripled what we now consider a kind of a sustainable annual harvest. So a lot of this, again, you think about this, so because they were focusing on sustained yield, they're also focusing on timber production, getting back this idea of succession. Then one of the things, if you're managing just for timber, high volumes of timber that you can continually renew on relatively short intervals, shade-intolerant trees make sense, right? They grow fast, they grow straight because they're trying to they're investing a lot of their energy into height growth, so they make nice wood products. They're not too branchy, their lower crown gets shaded out, they grow very quickly, they don't live very long. You can cut them in a way that means a lot of sun on the understory, say a clear cut, and you can get a new generation of intolerant trees coming in again underneath. So all of this kind of led to a focus on shade-intolerant early successional stands in the lower missions where a lot of the cutting happened. So short rotation lengths, 60, 80 years, depending on site. Don't let succession develop, reset it as if it were a fire or something else, and just get a new group of shade-intolerant trees. So even age, shade-intolerant management. So this added to that homogenization of the landscape because now a lot of our stands, they were either 1910 or when some of the last major fires, 1910 to 1930. Those were some of the last major fires here on the reservation, to a large degree. Or they were from timber harvesting in this period or in this period. So we've got a lot of stands, a relatively large number of stands and a relatively few number of age class and species compositions. At higher elevations, a lot of the focus where fires were not so common was a focus on a single tree selection, just again trying to, just like in a cedar stand where I showed those 2 trees blowing down, well, instead of letting them blow down, maybe they're cut, but a similar gap is created. So a few trees are cut here and there. And this also lets succession continue, this sort of Clementsian succession establish. But with fire suppression, what that means is that a larger proportion of the higher elevation stands are in older age classes. It's kind of almost a reverse of what we saw for the lower elevations, where there were more younger trees and fewer large trees. It's actually kind of reversed up high, but it's also resulted in denser stands. I don't have a whole lot of time, so I'm going to go through this quickly. This just kind of explains why so much of forest management, especially for timber, focused on younger trees. As a tree gets older, this gray area is the relative amount of energy it invests in growth. As a tree gets older, as a group of trees gets older, the overall energy they put in respiration and metabolism increases. The amount left for investment in growth decreases. So this is why timber sustainable timber management, the efficiencies you might cut in an age somewhere right about here, where you can get a new stand of young, quickly growing trees that are investing a lot into growth reestablished. So that's a lot of ecology and stand dynamics and history, and what does this have to do with some of our forest health issues? Well, fire suppression has allowed succession to advance. It's basically, again, interrupted what we consider the historic range of variability of fairly frequent low-intensity fire, especially at lower elevations. This means we've got more Doug fir, more shade-tolerant species. We have a higher density of species than we used to. Even age management has also done this. It's created a lot of stands that are between 50 to 70 years old. This is that stem exclusion phase of stand dynamics where you get a lot of trees competing for resources. So we've created a lot of stands in both cases, both through fire suppression and through some of our timber management. We have our legacy of both of these things are a lot more of our landscapes in fairly dense stands in that stem exclusion phase. So what that really means, and again, this is from the Tribal Forest Management Plan, you're seeing over time a buildup of trees per acre, an increasing amount of forest density. So getting back to this, how do trees invest in energy? If high densities means more competition and the trees are kind of competing with each other just to get enough sun, water, especially, carbon dioxide is not very limiting, especially with climate change. There's actually a bit more of it out there. But sun and water and nutrients are the limiting factors. If they have less of it per tree because there's more trees, then they're not investing down here. And that means that it's a lot easier for both native and non-native pathogens to really get moving in these stands. And since we've lost a lot of the stand diversity, if a bark beetle buildup happens in a 60-acre block, but there's other stand conditions, there's a burned over area here, that's going to check the movement of that bark beetle. But we've increased density, increased stress and competition in stands, and we've also made these stands kind of bigger and more homogeneous, which means we've created kind of the China buffet for bark beetles, basically. So limited investment down this priority chain, larger stands in similar conditions, creates this kind of optimal environment for some of our problems. And now, the double whammy, the added impact, this is a scientific term, although as Bill Sweeney pointed out, no one talks about a single whammy, so I don't know how you get to double, and I have yet to find a triple whammy. But the changes associated with climate change are really exacerbating these problems. Drought. Well, if a tree needs sun and water in order to make food, and we're seeing higher summer temperatures and increased drought, we're also seeing, especially in Montana, what the models are showing is over time, we're not going to get so much less overall precipitation, but we're going to get less of it as snow, more of it as rain. And what that means is spring rains and fall rains aren't contributing to that snowpack that's moving through the water table and the streams down slope and adding the soil moisture into the summer. So we have less kind of moisture working its way through the system in the summer. We have higher summer temperatures. This creates drought and it also increases fire danger. in terms of fisheries, this is a big problem because that reduced snowmelt means that the temperatures in the streams are getting warmer earlier. And especially for trout, which are so sensitive to water temperatures, this is a big concern. So all of these things, and added to that some changes in temperature distributions, which I'll come back to in just a second, are really taking this pattern, fire suppression, some of the timber management stand structures that we've created, add on top of that this new series of related stresses. It's really kind of, they've combined to create a lot of the forest health problems that we think of. And one of these is bark beetle. One of the things that we really try to emphasize here at the college is that bark beetle, we don't want to eradicate bark beetle. Bark beetle is a native part of our ecosystems. It's part of that stand structure. It's part of the things that cause disturbances in stands. Killed a few trees here or a group of trees here and let fire come through. They contributed to that patchy mosaic pattern from some of those older photos that you've seen. They kind of helped fire get into those stands. But what we've got now is sort of an epidemic. We're outside, again, this historical range of variability. It used to be beetles killed, across the landscape less than 1% in sort of patchy pockets. And now if you've driven over to Helena and you've seen the east side of that range you go through, there are thousands and thousands of standing dead acres. In Colorado, I think it was 1.5 million acres of dying trees from bark beetle outbreaks. Well, one of the things that we've done, again, kind of getting back to this sort of questionable China buffet metaphor, is beetles really like dense stands with low resistance, 14 to 18 inches in diameter, ages 60 to 100. Well, we've been putting out fires for 70 years. There was a lot of heavy cutting back in the 20s and 30s. Those stands are going through succession, and they're in dense stands, 12, 14, 15 inches in diameter. We're adding drought on top of that. And over the last couple of decades, and if you ever get a chance to see Steve Running talk about climate change, Steve Running from the University of Montana, he's got a great graph about Montana and winter temperatures. And the thing about bark beetles, they live underneath the bark over winter. And if you get temperatures of -20 to -30 Fahrenheit, even for a day or two, even once every 5 or 6 years, that will help limit the population buildup of bark beetles. It'll just freeze them out enough that it'll kill off part of the population. Well, it used to be that that sort of thing happened once every 4 or 5 years, and over the last couple of decades, those critical freeze events are becoming less and less common. We're seeing them now once every 10 years or every 20 years. I think I can remember one day in the last 8 years where it got down to -20. And foresters all over Montana were calling each other. We get excited about strange things, I guess. It's like, those beetles are going down! But it was rare. It was getting rare enough that it was something to get excited about. So what can we do about this? And there are management options. We can thin. The thing about thinning is it reduces stand density. It immediately gives more water to the trees you leave behind. And it allows those trees you leave behind to grow their canopy into the gaps and create more leaf area to make more food so they can invest further down that chain of investment. When in forestry at its best, when you see a timber operation, the trees that are being removed are the trees that are not optimally suited to the environment. What we're trying to do usually when we're doing forestry at its best is the trees that are being left behind are being picked first. These are the trees that we want to leave. The other trees we'll remove to give those trees more resources. So thinning, if it targets good, healthy trees, it helps give them more resources so they can defend themselves, grow faster. This can help with bark beetle. There's also some fascinating research that shows that the diameter of a tree is directly related to how far a bark beetle will fly. So in a 12-inch tree, the bark beetles will only fly and disperse to other trees about 30 feet. So if you thin in space to 35 or 40 feet, you can actually kind of mess up their ability to move from tree to tree. So thinning helps. Increasing landscape heterogeneity helps. Again, trying to create some landscape diversity so when bark beetles get established in one stand, they're not ripping across the landscape. One of the other things we're seeing a lot of right now is root rots, armillaria, gnosis, other root rots. You notice these mushrooms, you'll see them in the forest. Armillaria mushrooms, they're called honey mushrooms. They're edible as long as you don't mind eating a tree root rot. Kind of ruined it for me last time I had one. But they, again, are a native part of the ecosystem, but drought especially, these tend to be happening in shade-tolerant stands, cool and wet fungus love these sort of, cedar type, multiple layered canopy stands. They get going, trees graft root to root, and the fungus can move through there. What's happening again is especially we're getting more Doug fir in the lower elevations. Doug fir is very susceptible to root rot. We're getting larger, bigger, older trees in the upper elevations because of single tree selection and fire suppression, susceptible to root rot as they get older. Then you add on top of that drought from climate change. That tends to really stress trees, and it tends to enable root rot. Trees that are stressed with drought, that are shade tolerant, are very prone to root rot. What can we do? We can thin again because it'll give the trees more moisture. We can try to get, at least in the lower elevations, we can get fire back on the land, try to get these back into pine stands that are fairly open. Those stands historically were never prone to root rot. Pine's not susceptible to root rot. We can also manage within a historic range of variability. Again, we can, if we have to, we can reset some of these stands with root rot to earlier successional species that don't get root rot, or again, we can kind of create some landscape diversity. Now, a non-native that we're having a lot of trouble with, and this is a photo that Pat Hurley took here on the reservation. I can't remember exactly where this came from, but this is a pretty common sight. You see a lot of these standing dead white bark pine. White pine blister rust is an introduced pathogen. It only affects what we call the soft pines or the white pines, pines with 5 needles. It was introduced on the East Coast shortly after the turn of the century, where it affected eastern white pine. It's had a big toll in our western white pine, but especially our white bark pine. These are pines that live right at the top. These are the subalpine, right at the edge of the tree line species. Very stressful environment, short growing seasons, cold temperatures, heavy winds. You add an introduced pathogen on top of it, you get a lot of problems. The white bark pine is dying out. This is a huge concern. This is a species that we call a keystone species, not named after the beer, but after the architectural concept, the middle of the arch, the keystone. You pull that out, the arch collapses. We think white bark pine might be one of those species that if it goes away, those really kind of marginally stressed environments, this could lead to a breakdown in the whole ecosystem. The food, their seed, are a lot like other pine nuts. And if you've ever eaten pine nuts, which most of the commercial pine nuts are from a Korean pine or other pine, but white bark pine is similar. 2 to 3 tablespoons of pine nuts, enough to kind of, just barely fit in the palm of my hand, it creates 30-40% of an adult person's protein and fat needs for a day. So you think about that for mammals, bears, and other species making an existence on these high elevations. They also help to anchor snow and soil, slow down snowmelt. Losing these species could have a huge impact. Losing white bark pine up high can have a huge impact on ecosystems, all the way down the mountain, basically. So global warming is aiding competitors. Fire suppression is actually also allowing succession to happen. So not only are these trees getting attacked by diseases, but other more shade-tolerant species are coming in underneath because of warming and because of fire suppression, which is adding to competition, which adds to stress. What we can do here, kind of sometimes when appropriate, let fire do its job at higher elevations or restore fire. And then there's a lot of work, Glacier and other places is working with disease-resistant individuals, trying to find those few individuals that don't seem to succumb to this disease. And then they're taking seed, and actually they have greenhouse operations going. And then they're packing those seedlings back out into the backcountry and trying to do some kind of lifeboating where they're getting disease-resistant genetics out into the backcountry. Okay, so summing it up, past management objectives, fire suppression partly, and succession in general create denser stands. The stress just creates basically more susceptible stands because of those densities. Climate change is exacerbating that stress. And in a lot of cases, we can let this process continue. We're always going to have forests. It's just a question of what forest structures, what forest types do we want. And now that we're learning more about ecosystem dynamics and historic range of variability, active management really does hold a lot of options to trying to get diversity across the landscape, age class diversity, species structure diversity, back into these systems. So they're basically back within a historical range of ecological variability. So I hope I haven't gone too long. It's always a danger when you give somebody who's used to lecturing for an hour and 20 minutes the mic. But if there are any questions, I'd be happy to take them.
Adrian, that one picture you showed with all the different colors that was from the Forest Service, is that the diseased trees?
Oh, yes. Let me, if I can back up there. That is, right, getting there. There it is. This one?
Yes.
Yes. So this is actually bark beetle infestation. So these are what we call red and dead. With the chlorophyll dies, it leaves a reddish brown color in the needles. So, and you can see even here, there's a patchiness on the landscape. I mean, there's some bigger mortality than we would want, and the fire that gets going here, and all this dead timber is probably not necessarily going to stop at the boundaries. But you can see that either because of species diversity or age class, some stands are hit harder than others. Was that?
Yes. Is that around here, or is that Colorado?
This is Colorado, I think. I was trying to use as many local photos as I could, but this is an internet picture. It was Colorado. But we do see these patterns here. The reservation so far, we're not seeing a whole lot of this yet. We're seeing it in upper elevations and lodgepole pine stands, but then they tend to live to about 80, 90 years old, and then they catch on fire. They have cones that are sealed shut with pitch. When temperatures exceed 170 degrees, those cones pop open, and then the seed rains down on the site afterwards. So they're kind of fire adapted. So seeing some of those pockets are red up in the missions, the smaller pockets that are old lodgepole stands, they're actually just getting set to do what they always do. The problem would be if we put out those fires, then we're going to get shade-tolerant species replacing them that didn't used to do that. So, yes?
So we were always taught that trees can resist pests and insect infestations by the chemicals that they produce.
Mm-hmm.
And do people see that happening with the pines, where the insects are, getting into them?
The pine's defense against bark beetle is pitch, that gummy, the tree resin. And when the bark beetle bores through the bark, the tree basically tries to pitch it out. So it tries to gum up the beetle, because once the beetle makes it through the bark into the phloem, which is the tissue right under the bark where all the food moves through, it'll start to mine through there and lay egg galleries. And then the larvae will hatch and they'll spread out. And then eventually that larvae will turn into adults and they'll bore back out and fly to another tree. So if a tree can create enough pitch to stop the bark beetles getting in, it can defend itself. But when you have a high density of trees, each tree's not getting enough energy, enough water, making enough food to create enough pitch per tree. And that's where we see the problem. So these dense stands where the trees are so busy competing for resources that they're not necessarily creating enough, they're not investing down to that defensive chemical, to that lower investment priority, then they can't defend themselves. Because bark beetles are kind of like, they hunt in packs in a way. They're fascinating because they release one beetle we don't quite know how they can detect stress, but they can detect stress in a tree. And one beetle will release this pheromone that tells other beetles to come to it, and then they mass attack that tree. So if the tree doesn't have enough pitch to defend itself against 40 or 50 or 60 bark beetles, it's going to succumb. And then actually, then the beetles release another pheromone that covers up the first one. So beetles stop coming to that tree, and then they move out and look for other trees. So it's a very fascinating system.
Thank you.
One pest you didn't talk about was bloodworm.
Yes.
So how does that fit in?
Similar. I was thinking about that, and I knew I was going to run out of time, so I didn't sneak spruce budworm in there. Spruce budworm, actually, his favorite foods are the true firs. I don't know why it's called spruce. It could be called fir budworm, but it likes the more shade-tolerant species. And again, it's a defoliator, so it eats needles and leaves, especially early spring. But once we're building up it likes Doug fir also. We're building up, again, because of fire suppression, we're getting more of these more shade-tolerant species. So we're seeing higher densities of grand fir and Doug fir So we're creating more food for it, basically. We're creating, again, fairly dense, somewhat stressed stands, lower species diversity. You know, spruce budworm outbreaks, if Doug fir is in grand fir, 1 tree out of 4, you don't see an epidemic. You just see individual tree mortality. But when 70% of your trees are the food type that that insect likes, then its populations build up and it can get a run on things. Does that make sense? Any other?
Are they resistant? Oh, sorry.
Oh.
Somebody else. Are they pesticide resistant? Are they finding ones that will, next generation, resist the pesticides if they're using those?
You mean?
If they pesticide the trees.
You know, mostly, there are some pesticides that are used for these, but because of the scale of a lot of these problems and because you have to pretty much drop them from the air to get any kind of density, and because of the water implications, a lot of managers, especially the tribes and the national forests, have moved away from mass use of. So they do offer alternatives, but generally people have tried to go more back to this integrated pest management where we try to reduce stress and change species diversity and things like that.
What's the marketability of damaged trees like that?
If you get them out before, the thing about beetles especially is, if you've ever seen blue stain in pine, that's actually a fungus that's brought in on the back of bark beetles. And as the beetles move into the tree, they have a kind of a symbiotic relationship with this fungus. And if it gets warm, once it gets warm, that fungus really, this population starts to go and it starts to attack the tree. A lot of people don't like blue stain in their wood. It's a very low market value. So you can salvage trees like this if you cut them pretty much before the summer after they die. So that's a very short window, as we have, you know, especially with NEPA and, you know, having to do environmental assessments or, you know, any kind of planning, go through a public scoping phase, especially if there are people who are resistant to the idea of salvage on this scale. Frequently, it's almost impossible to do a salvage, at least on some ownerships, in the time necessary. But it is possible. And the tribe here after the Chippy Creek fire, I mean, it was amazing the salvage the work they were able to do. And it kept beetle and fire from building up in those stands. I mean, from a management point of view, I think they cut 50 million board feet. Their annual allowable across the reservation is 20 million. But because of the fire mortality, they cut over double their annual harvest in one place. But it was to get those trees out before we saw it setting up for the next big disaster. So, Bill.
It's my understanding that the trees, as long if they're dead, as long as they're standing, that's less of a fire risk than when they fall down. Is that?
It is true, I think, to a degree.
Fire risk is going to stay with us until those.
Rick, do you want to? I defer to my learned colleague and wildland fire science instructor.
They're more of a threat. This is the old thoughts. They're more of a threat while they're still standing. They still have their needles. The needles act as the big problem for the first 5 or 6 years. Right. However, people are just now finishing up a couple of different studies where they're finding out that the red dead, standing dead versus just the standing dead, they're both going to burn. Overall, it really depends on where you're at as far as your higher elevations, lower elevations, what kind of decomposers you have in the area. But a lot of those standing dead could stay standing for 100 or 120 years. We still have standing dead that are left from the 1910 fire or forest around here. So they will add to the what's called the surface fuel component. During an extreme fire event, it's not going to matter. The fire is going to take it no matter what, whether it's standing, whether it's on the ground. And these lower hazard fires that people are trying to use for wildland fire use or wilderness fire use, whatever you want to use the acronym, where they want to let it burn, then it becomes a consideration because that's going to feed into the overall behavior, whether or not it's going to stay a nice tame fire, if you want to put it that way, or it's going to wind up being a suppression problem.
An excellent ecological answer to it. There's a lot of it depends in there, which which is sort of the mainstay of good ecological answers. Okay.
So obviously I have a question about water, but the tree needs water as a resource, but do we see in these stands in the northern latitudes here where the water is primarily for the tree coming from precipitation, or is it snowmelt? Without snowmelt, with climate change, are there going to be stand changes, and what's the strategic planning for that?
Yeah, there's going to be strategic planning. I think we're just beginning to try to get there. Again, it's going to depend on everything from aspect and soil type and range and where you are in the elevation gradient. There are going to be changes. Just to give you a little bit of reference, one of the numbers that we use in class is a tree will transpire in one day in photosynthesizing and just water loss as it brings in carbon dioxide. A tree will go through 40, 50 gallons a day. So what you actually get when you get mass mortality like this is you see an increase in soil moisture. And of course, you get increased quantity but loss of quality because it's flowing through the system faster and everything else. But to answer your question, it's both precipitation and snowmelt. So there's a couple of different patterns there. The thing that we're really worried about, especially at lower elevations, are that late July, early August period. The most limiting thing for ponderosa pine establishment of little trees is soil moisture late July, first couple weeks of August. And that's got more to do, I think, at that point with precipitation and snowmelt, especially lower elevation. Higher up, it's a combination of the two. So it depends, just like I said before. But
when you add fire back to the mix, then your water doesn't go into the soil as much. It likes to tend to run past where it's needed. So how is that going to exacerbate the problem?
Well, again, you got to think on a landscape level because hopefully we're trying to avoid fires in stands like that, right? What we really want is that patchy mosaic pattern that we showed, where there are these kind of scattered areas, and yeah, the rain, you are going to get more erosion or more movement across a couple 100-acre burn area than you would, but then it's going to hit another forest area and it's going to slow down, right? So it's just going to kind of redistribute it. Hydrophobicity, when a fire burns hot enough in a sandy soil that it kind of turns water repellent, is fairly rare. So a lot of it is just because there are no trees to intercept that rain. The rain drops are hitting the ground directly. You get splash erosion and things like that. But for one thing, a lot of these sites you'll get vegetation next spring. It's amazing how quickly these things green up. So you've got that one winter, and if you keep them in smaller acreages, you're not going to deal with the kind of a massive landscape problem of flow through and loss for any significant length of time that you might if you had watershed level fires. Did that answer your question? Amy. Well, thank you very much.